Dear viewers, welcome back to our channel Last Minute Electrical. I am Soikat Ghosh. In here, we will discuss the power electronics. In this particular video lecture, we will cover the full topic, all topic of power electronics. In the first video, we already discussed everything about diode. In the second video, we already discussed a few topic regarding the thyristor. In this particular video, we will discuss some part of thyristor which will remaining. What is those? What is the latching current and what is the holding current, then turn off characteristics of thyristor, then thyristor gate characteristics, then thyristor rating. After that we will discuss how we can protect the thyristor in time of its operation, and last one is what is the requirement of the series and parallel operation of thyristor and how we can perform that operation. This we will discuss in this particular video lecture. So let's go for check what is the latching current and what is the holding current. So this is the latching current definition. What is this? First we read the definition of it. Definition is that latching current is defined as the minimum value of anode current which is must be attained during the turn on process to maintain the conduction when gate signal is removed. What does it mean? It means that always we know when the anode is positive, cathode is negative, in that time gate signal is required to turn on the thyristor. But in here it must be says that when the anode is positive, cathode is negative, in that time when we apply the gate, anode current should be reached to a minimum value. Then if we remove the gate signal, then also conduction will never off. What does it mean? It means if suppose let assume a practically value, let take up latching current is 10 ampere for a particular SCR. So in time of it triggering on by the gate signal, when the gate signal is applied in the turning on process, then anode current should be reach more than 10 ampere. If the anode current is 9 ampere and by applying gate signal conduction begin, and after conduction begin, when we remove the gate signal, if the anode current is still 9 ampere, then the ACR will be off in the time of removing the gate signal. But if the anode current is more than 10 ampere in the time of triggering on, if after that if we remove the gate signal, then the thyristor will not off. So anode current should be reached to its latching current level when the gate signal is removed to maintain the conduction, that is known as the latching current. Okay, so this is the now holding current. So this is holding current definition is that holding current is defined as the minimum value of anode current below which it must be fall for turning off process. Means what? Anode current, suppose anode current should be reached when the conduction is going on 50 ampere, let assume. Okay, so when we try to turn off the thyristor, this current should be reached to a minimum value, that is known as the holding current. When the current means that anode current reached to that particular value or below of that particular value, then only thyristor will be turned off. Suppose the holding current is 8 ampere. So when the conduction is going on a load over there, suppose there is 50 ampere passing through the anode, current is now 50 ampere. So for turning off the thyristor, that 50 ampere should be come to the 8 ampere or below of 8 ampere for turning off the process of SCR. So that is known as the holding current. So this is the minimum value of anode current below which it must be fall for turning off process. So this is known as the holding current. Okay, so let's go for the next one. Next one is our turn off characteristics of the thyristor. This figure you are already familiar if you are already follow the lecture 1, because this is the same as the diode turn off characteristics that already we discussed in the first video. So let's discuss over here once more. So what is actually it? Actually a thyristor or diode, whatever is the device, they are combined with the semiconductor material. They are made by semiconductor material, and when they are using the semiconductor material come to the act of the current flowing, it capable to store some energy. So when the ACR is off or supply is off, then what will be happen? Current should be goes to 0. In here current you see goes to 0. Current goes to 0, but in here current will not stop at this particular point, because when current goes to 0, supply is disconnected, then whatever the storage charge inside of the thyristor, that charge that start discharging. So when the storage charge is start discharging, they create something like this type of curve and again goes to zero. But it take time, huge time to take goes to zero. That is why we consider this particular cycle up to 25% of this peak value. This is the peak value that is denoted by IRM, and this is the 25% of IRM. Means we are, if this is our 100 IRM, suppose I assume this is the 100 ampere, then we consider this turning off characteristics time period is started from this zero crossing. When it reached to 100, then it reached to 25% of 100 means what, 25. So it consider the time period 0 to 25 ampere. If the peak value of current is 100, then only. If peak value of current is 200, then we consider 0 to 50 ampere time period is as the turn of characteristics. So from this zero crossing to particular this point, means when it reached to its peak value, this is known as time period TA, and its peak value means IRM to 25% of its peak value is known as TB. This total time period is known as TRR, means TRR means what, TA plus TB. So this is known as TRR, and there is also a quantity, also a factor, what is known as that is soft factor, which is known as TB by TA. There is a derivation for finding out the reverse recovery time, means the value of TRR, and the reverse peak value of current means IRM and TRR. There is a derivation to find out IRM and TRR that already discussed in the dark part. You can check from our first lecture. Okay, so let's go for the next topic. In the next topic, we will see the thyristor gate characteristics. What do you know? For turning off a thyristor, we require a gate signal. So in here, we are varying this gate signal as per some deserving on the basis of some conditions. Okay, what is those condition? In the first case, means suppose just assume the red line, just look at about the red line, it means number 2 graph. In number 2 line, in this number 2 line, what we see, we are trying to minimize the value of current and maximize the value of voltage in the gate terminal. Means what, we are increasing the voltage with keeping constant the current, trying to keeping constant as minimum as possible the value of current. Then we get a line just like 2. In the first line, what we got in here, we are trying to maintain as minimum as possible the voltage value and trying to increase the current. Then we got the line number 1. So this is the line number 2, where the voltage is maximized, current is minimized in the line number 1. When current is maximized, voltage is minimized. So in this way we get 2 curve. Okay, so in here we got a line number 1, and this is the line number 1, the green one, and the red one is the line number 2. So in here, every SCR has a minimum value of required gate voltage and the minimum required gate current. In here, OA is the minimum required gate voltage. Means for triggering on a gate or triggering on through gate signal, we have to maintain a minimum voltage which is OA. In case of current, we have to maintain a minimum current of OB. So this much current should be required and this much voltage should be required in time of triggering on SCR through gate signal. And also gate terminal has a permissible maximum gate voltage and maximum permissible gate current. The maximum gate voltage is VGM and maximum gate current is IGM. So enter these two lines are come to particular this part E to Z, because after Z point if we apply the gate voltage that is above the permissible gate voltage, if we apply below the E point voltage, then that is the under the that is not satisfy the minimum required gate voltage. Same as the entire one line are come to only this part C to F, because after F after if we apply the current that is above the maximum permissible gate current, and if we apply the less than current from the below point C, that will not satisfy the minimum required gate current. That is why it start from C, ended in F, and in here it started from E, ended with the Z point. Okay, so now there is the rated gate power dissipation also over here for a particular area, that is this black color line, that is denoted by PG, rated gate power dissipation. Means there should be a power limit. So by joining every point, we get a particular area that is covered by E, D, C, F, G, H, J. Means this sketch area is known as the preferred gate drive area. This sketch area is known as preferred gate drive area. Means suppose when we want to drive the gate, the voltage and current value should be come across any point under this sketch area. So that is the preferred gate drive area. Okay, so when we try to Thyristor gate characteristics, find out gate characteristics and trying to trigger a SCR, then we should remember one thing: the value of voltage and current apply the gate terminal, that should come under this sketch area, preferred gate drive area. So that is a very important thing, because if we apply the voltage current is not inside of this sketch area, that may cause the permanent damage to the gate terminal of the SCR. Okay, so next let's go for the next topic. So this is the Thyristor rating. Suppose when we buy a Thyristor, suppose in time of buy a Thyristor, there's some we got a data table. In the data table there specifies lot of things, so we have to understand everything before installing the SCR for your particular project. The full details of the rating on the basis of the subscriptions. Okay, if suppose first subscription is D, that is denoted the forward region. If the first subscription is denoted by R, that is known as reverse region. In case of the second subscription is W, then that is known as the working value. If that is known R, that is known as the repetitive value. If in case of the third subscription, if M, that is known as the maximum value. Okay, so this is the first subscription, second subscription and third subscription. So let's come actually what is it. Suppose let us assume that is denoted V, D, W, M. So V for what you know, voltage. D means first subscription is D, so D is the forward region, that's something in forward region. W over here, that is under the second subscriptions, that is, so W means what, working value. Okay, in the third subscription, that is the known as the maximum value. So VDWM we can say the maximum forward working voltage. M stands for maximum and M stands for maximum, D stands for forward region and W stands for working value. That is why we called it maximum forward working voltage. Okay, and in case of VDRM, now look at here, VDRM, D stands for what, forward region, R stands for what, repetitive value, and M stands for what, maximum value. Okay, so VDRM is known as the repetitive forward working voltage, repetitive forward working voltage. In here, why now may question what is this actually? Actually, in case of our practical circuit that containing many of capacitance, many of inductor, different type of load. Okay, so that may some transient period come over here where this particular time the capacitor may discharge, inductor may store some energy. That is why there is some spike and this type of thing come to the act. That is why when that is the repetitive means every same time, every the peak value is same, then that is known as the repetitive case. Okay, suppose this is not repeating in any cycle, so that is known as surge value, surge forward value. Okay, DSM, that is known as voltage, DSM known as maximum surge forward working voltage. S stands for surge. I am sorry to forget written over S, so you just think in the second subscription one more thing is here, that is S, that is known as surge value. I am sorry for it. Okay, so now let's go for look at the reverse part. In here, what is given over here? VRRM. RRM. R in the first subscription, R means what? Reverse region. In the second subscription, R means what? Repetitive value. In the third subscription, M means what? Maximum value. So VRRM can be written as maximum repetitive reverse working voltage. Okay, in here reverse maximum repetitive reverse working voltage. Okay, in here in the second part is what? RWM. R for reverse, W for working, M for maximum. So that is known as maximum reverse working voltage. Maximum reverse working voltage. In the same way, VRSM. VRSM means what? R means reverse, S means surge, which I forget to write over here, M is the maximum value. So VRSM is known as maximum surge reverse working voltage. In this way, we can find all the value from their data sheet, and whatever we circuit are using, we have to find the value, the practical value of VDSM, means circuit value of VDSM should not exceed the value of data sheet. So in this way we can use our Thyristor as per from the rating and as per our desirable rating. Okay, in this way, if we after all this checking, if we buy the Thyristor and if we use the Thyristor, that there is Thyristor never be damaged. Okay, otherwise if you use a Thyristor which dataset DSM value is less than your practical value of circuit VDSM, means suppose once time will come when the surge value is more than its working Thyristor working surge value, then Thyristor will be damaged. So we have to look at this particular point before using a Thyristor. Okay, so this is one part of the Thyristor rating. So let's go for the next slide. About the look in here, the Thyristor protection. Generally in here there are various type of protection over there. In here we are specific discuss two particular protection. One is known as di by dt, another is dv by dt. In here di by dt protection means what? Rate of change of current with respect to time. Means what? Sometimes it happens in the circuit that for a particular time period current will be very high and then again current will be come to its normal value. So in this time ACR may face some problem. So that is why we have to give some protection from this di by dt. What we do for protecting our ACR from a di by dt protection? We have just connected a simple inductor in series with the circuit, means anode current. What will be happen? We will not showing the circuit over here. What will be happen? Suppose this is a ACR. In here we are connecting an inductor over here. Then what will be happen? All we know, the L means inductor is always oppose the rate of change of current with respect to time. So it oppose the di by dt, means it delay the rate of change of current with respect to time. So in this way Thyristor will protect it from the di by dt protection. That is the simple thing. Now we look at here dv by dt protection, means what? Rate of change of voltage with respect to time. This is we generated by help of a snubber circuit. What is the snubber circuit? So this is the circuit diagram of a snubber circuit. So this is the ACR, this is a supply, this is a load, and there is a switch we are using, and this RS and CS is a part of the snubber circuit which is connected parallel with this particular ACR. Okay, so when this switch is sudden closed, then what will be happen? The voltage across ACR suddenly come to this much of voltage Vs, means 0 to Vs come within a very short time period. So that may damage this ACR. So how we can protect this? So in here we are using a capacitor. At the time of the starting, capacitor is fully discharged condition we are installing over here. Capacitor is on discharging condition, there is no charge inside of it. So capacitor has initially charged how much? 0. So when this switch is closed, then what will be happen? When the capacitor is initially zero charge, then it provide a short circuited path. So majority of the voltage changes dV by dt is applied across the CS, means then capacitor now charge itself. Okay, so across the dV by dt, the entire dV by dt are majority come across the CS, and a very less amount of dV by dt come across the SCR. So in this way SCR will be protected. So for protecting the SCR, whatever capacitor we are using, we have to remember one thing, that capacitor should initially charge is zero, so that is act as a short circuit. Now the question may rise, so what is the function of this RS? RS is the function is that when the capacitor is fully charged and SCR is triggered, conduction begins, means there is some current flow is going on over here. So in this case what will be happen, this capacitor when fully charged, then it start discharging. So in this way capacitor charge discharging across this terminal, whatever arrow is given means anti-clockwise, because this is goes to positive plate and this is goes to negative plate after full charge. So in this way when current passing through this SCR, that may face a huge amount of di by dt or huge amount of current passing through this SCR, because the supply current and the capacitor current, that is why RS come to over here. This resistance will limited this value of current discharging by this capacitor. So this is the entire syllabus circuit. In here in the syllabus circuit, main two thing is RS and CS. CS is initially charge is zero, acting as a open circuit, sorry, acting as a closed circuit. So whatever the applied voltage that for the initial time, that is major part of that applied voltage across this CS and very less amount across this SCR. So that is why the SCR will be protected from sudden dV by dt by using this syllabus circuit. So this is the two protection, di by dt and dV by dt. These two protection is the one of the important thing. There is various protection thyristor already all have. These two discuss over here. One is di by dt, another is dV by dt. Okay, so let's go for the series and parallel operation of thyristor. From the 1957, the time of SCR invention, research is continuously going on to increase the voltage and current level of SCR. As an outcome of this research, today we got a maximum 10 kV and 3 kiloampere rating of SCR. But when we thinking about the industrial application, this rating of 10 kVA 3 kiloampere is also not sufficient. That is why sometime we have to connect series and parallel. Series connection we use for the increasing the voltage level, and parallel we are using for the increasing the current level of SCR. So we can say in this way SCR used as a string, means there are many SCR we are using in the series or many SCR we can use in the parallel for increasing its voltage and current level. So that is the when there is more than one SCR in a particular series or a particular parallel combination, that is known as the string. So what is the string efficiency? We can say string efficiency is the actual voltage and current rating of the whole string, and that should be divided by the individual voltage and current rating of individual SCR multiple, that should be multiplied with the number of the SCR in the string. So ideally the actual value of current and voltage and current rating of the entire string should be equal to individual voltage current rating of the SCR into number of the SCR should be same. So these denominator and numerator and denominator should be same. So that is why ideal value is always 1. But practically what we see, the practically this value is always less than 1. Clear? So that is known as the series parallel operation of the thyristor. So now we will check the particular series operation and what is the problem of it and what is the solution. In next we check the what is the actual parallel operation and what is the problem and what is the solution of it. Okay, so let's go for it. So when we operate in the series operation or parallel operation, means string operation, then we have to know one thing is that for getting the maximum efficiency, all ACR particularly in that string should have same or identical VI characteristics. In this particular point, this should be noted that if suppose two ACR1 and ACR2 have the same VI, same voltage and current rating, they have all rating as same, but also they don't belong from the same VI characteristics. Means what? If suppose 2 or 3 ACR all have the same VI, same the rating, they should not come under the same VI characteristics. So that is the problem in case of the series or parallel operation. Let's check what is the actual problem. Suppose in here we are discussing the series operation. In here there is one ACR and another ACR connected to it, to one ACR1, ACR2, they are connected in series for increasing the voltage level. Okay, so when they are connected in series, the current across this whole string should be same, that is denoted by IO. These two ACR has the same rating, but their VI characteristics is not same. This is the only in here, only look at the forward part. Okay, because that we are not discussing about reverse part, so that is why in here we are just draw the forward part of the VI characteristics of ACR. So this is the number 1 and this is the number 2. Look at here, in this particular case the breakdown voltage, the forward breakdown voltage for the both ACR is same, but for different value of current. Means what? Their rating should be same, but VI characteristics is different. What does it mean? Suppose let's take a particular current passing through here, that is IO. If suppose this much current is passing through this string, then what will be happen? First case, in the first ACR, how much voltage apply across it? Now V1. In the second ACR, how much voltage is that? This is V2. Means what? For the same rating of ACR, for a particular current, they are blocking and they are dealing with two different voltage, that is V2 and V1. So we can say the leakage resistance for the ACR1 is V1 by IO, and the leakage resistance for the ACR2 is V2 by IO. Okay, as per the diagram, we already can see that V1 is higher compared to V2, that is written over here. So in here, practically, actually this ACR1 and ACR2 block how much voltage? V1 plus V2, simple thing. But as per the rating, if we since about the rating of ACR1, as per the rating they are actually blocking that V1 into 2 ACR, that is why 2 into V1. Means what? We are telling is the number of individual VI rating of ACR, that is V1, and number of ACR is how much? 2, that is why it is 2V1, and actually they are blocking how much? V1 plus V2. So what is the string efficiency? V1 plus V2 by 2V1. So from here that we can written as half into 1 plus V2 by V1. By calculating this particular equation, you can get this particular equation. In here, what do you know? V2 is less than V1, so that is why this entire quantity is obviously less than 1. So we got a efficiency in less than 1. So how? That is the problem, the efficiency is less than 1. So now how we can increase the efficiency? So means I want to say what is the solution of it. So let's go for the solution of it. Suppose there are n number of ACR connected in this string in the series. In the first ACR, this is the first ACR. If we remove that part of ACR, how many ACR is remaining? N minus 1 number of ACR is still remaining in this string. Okay, so in this particular ACR, what we do for making the same voltage drop, means we want to equal V1 and V2. In here we are trying to equal V1 and V2. What is the solution? If we add a resistance over this terminal, if we add a resistance over here, then the voltage drop across the V2 is increases. When there is 2 ACR in the string, that may be created by a particular resistance, we can connect over here, and the voltage drop across V1 and V2 will be same, then the efficiency may further increases. Means that here we are trying to increase the value of V2, as simple as that. But suppose there are n minus of number of SCR over there, n number of SCR over there, then how we cannot calculate individual value of resistance for particular SCR. That is very difficult and hard work. So that is why we have to optimally find out in particular value of resistance which must be maximize the efficiency. Means what? We have to find out the optimized value of resistance which will be common for every SCR, means every n number of SCR, every SCR of the string. By using this resistance we can maximize the efficiency of the string. So how we can calculate this, how we can find this, let's check out over here. So let us assume in the first SCR current passing through here, that is the minimum current, and other SCR whatever the current passing, that is the maximum current through the SCR. So that is why we are written over IB max over here, and in here we are written IB mean over here, and the string current is same. I in here is also I, in here is also I. First case I is subdivided in two part, IB mean and I1. IB means coming through the SCR, I1 is coming through the resistance, and in the second case I is in here I is coming through this SCR and I2 is coming through this resistance. Same over here, I subdivided into two part, IB max coming through this SCR and I2 is coming through this resistor. This is the same thing for the n minus of SCR, because first SCR is already cancelled out. So in here how much voltage drop? Let us assume this is the VBM. Okay, this much voltage drop across here, because in here I1 is the major, I1 value is higher, because in here IB max, so I2 is less, in here IB mean minimum current, so I2 is higher. So that is why VBM is the voltage drop across this I1 and R. Okay, so I1 can be written as I minus IBMN, I2 can be written as I minus IB max, where I is the total string current. Okay, the voltage across SCR1 is VBM, which is known as VBM. VBM means R into I1, R into I1. So voltage across n minus 1 SCR is how much? N minus 1 into I2 into R, because every voltage drop, every voltage across the SCR is I2 into R. How many SCR over there? N minus 1. That is why it is written N minus 1 into I2 into R. So total voltage across the string is how much? Vs equal to, we can write I1 plus I1 into R plus N1 n minus 1 into I2R. So this is the total voltage drop across the string. So that can be written as I1 into R equal to VBM. We put the value of VBM, and n minus 1 R into I2. This I2 can be replaced by I minus B max. I minus B max. In this equation, in the next line, what do we do? This I replaced by this I in this equation replaced by I1 plus IBMN. Then we find out this equation. If this equation I replaced by I1 plus IBMN, then we got this final equation like this. In here, what do you do? VBM and VBM, it written as VBM n minus 1 R into I1, we are written over here. Another quantity we are written n minus 1 R into IB max minus IB min. So we are written this equation. In here R into I1 equal to, already we know VBM. So VBM plus n minus 1 into VBM. So that equivalent to n VBM. And in here minus n1 R IB max minus IB min, that taken as delta of IB. So that is why we are written over here Vs equal to n of VBM minus n minus 1 R into delta of IB. So from here we can find the value of resistance R equal to n VBM minus Vs n minus 1 into delta of IB. So that is the optimized value of resistance we find from here for getting the maximized efficiency of this string. So the for finding out this resistance value, every component of or every value of the ACR is given in data sheet. Suppose if sometimes IB mean is not given in the data sheet of the ACR, then we can assume we have to assume that delta of IB equal to IB max. So when we finding this value, if we put the same amount optimized value of this resistance for the every ACR parallel to every ACR, then we get the maximize efficiency. Then we get the maximize efficiency for the for the entire string operation. Okay, so this is the series operation, entire discussion about the series operation, where we see first we see what is the actual series operation, how we can operate in series, why we operate in series, what is the necessity of series operation, and what is the general problem in the series operation. The efficiency is less, and then we check what is the solution of it. The solution is to finding a optimized resistance value which will maximize the series efficiency, series string efficiency. Okay, so let's go for the parallel operations. So in case of the parallel operation, we are connecting the ACR 1 and 2 is for the parallel. So in here we are operating it in parallel for increasing the operating current value, So in here the same thing we are facing, whatever we have, same problem we are facing over here, what we are facing in case of the series. In that case, that is the only forward conducting mode we are drawing over here. So across these two ACR, they are connected in parallel. So the voltage across these two terminals, means voltage across the ACR 1 and ACR 2 is the same, that is the V2. But for that same voltage of V2, the current rating is not same. Means for the particular voltage V2, one drawing how much current I2, another drawing how much current I1. That is the problem in over here. So how we can, what is the problem for different drawing current I1 and I2? Let's check. This is the due to same voltage, same VI rating, but different VI characteristic. We are facing this for particular V2, one drawing I2 current, another drawing I1 current. So for the same voltage of VT, ACR 1 share I1 amount of current and ACR 2 share I2 current, where as per the diagram we see I1 is higher compared to I2. So actually to ACR draw the current, entire current, how much? I1 plus I2. Means entirely they combine how much current they draw, I1 plus I2. So but as per rating, how much? 2 ACR 1 and 2. So 2 into I1. So 2 into I1 is as per the rating. So this is the string efficiency in denominator and this is the numerator. So by calculating the string efficiency by the previous formula, we got the same thing, which is less than 1. So that is the problem. So now what is the solution of this problem? The solution of this problem is that when ACR, main problem is that when the ACR 1, suppose in here what you see, ACR 1 is drawing more current. So this ACR is drawing more current compared to this ACR, then what will be happen? If it's draw more current, the IR drop, means the voltage drop across this ACR will be higher compared to this. So when the voltage drop means what? I square, voltage drop means IR. So power drop is I1 square into R of this ACR. So then what will be happen? Temperature of this ACR will be increased because there is more current is passing compared to this. Then what will be happen? The temperature when increase this ACR, that will further decrease the resistance. So further increase of temperature means what? When the temperature is increased, it decrease the resistance. When the resistance is decreased, current value is further increased. When current is further increased, temperature is further increased. So in this cycling process, once upon a time it will come, the current will such a amount will passing through this thyristor that it will be damage. So in the what is the solution of this? If the temperature of these both ACR will be maintained at the same, then that may be a solution is in method of back calculation. So in here we are combine all the ACR of a string in a particular heat sink. So if we use a single heat sink, single or connected heat sink, single heat sink among the all ACR which is connected in parallel, then what will be happen? The temperature across the every ACR will be same. Then what will be happen? That push the all current passing through I1 near to I2. So in here, if we connect the every SCR on a single heatsink, that is the one of the finest solution of the parallel operation for the getting maximum efficiency. Okay. And also there is another solution is there to install the inductor over here and tap from the center of the inductor. Then what will be happen, if this side inductor current will be higher compared to this side inductor, then they will oppose the induced EMF with the each other. Then what will be happen, then the rated current of these two SCR I1 and I2 also will be same. But most effective solution is to use the heatsink across the all SCR connected in the string for the parallel operation. Then we got the maximum efficiency for this parallel operations. Okay. So for today, this is the end slide. This is the last slide. In the next class, in the next video, we will discuss the gate firing circuit, where we discuss the R firing circuit and RC firing circuit. Then we will follow to the Thyristor commutation process. Under there is two process, natural commutation and forced commutation. We will discuss all those things in the next video. For now, that's it. Thank you. Goodbye.